Okay, this is the video to help you analyze your Ester results. I'm going to explain what we would have done had we have done weeks 2, 3, and 4, and I'm going to go over the lab report form that you're going to turn in for this experiment. So first of all, let me go to the website. Let me go to Canvas and show you what is there. First is the laboratory format, which I'm going to go over. Then secondly is there's a copy of the experimental handout, which is there for your reference. Then there's a table of unknown esters that we will talk about that has the table of the possible unknowns as well as their physical properties. And then there'll be a link for this video, which isn't there right now because I'm recording this video. And then there's a video on how to measure the microboiling point, which we'll go over. There is a handout, which I'll show you the key parts of for that, and then the actual video of measuring the microboiling point. And then down below are going to be the NMR spectra for each of the unknown numbers, and we'll go over what 3x1 and 3x2 means in a moment. So that's what we're going to take a look at here. So going back to the PowerPoint and going back into the slideshow, prior to writing the lab report, I would like you to do the following. Number one, you're going to write the procedures and observations for the only week that we did, which was to do the reflux. So this is for doing the reflux. Then secondly, you're going to watch this video, which hopefully you're doing now, and it'll outline the procedure and talk about the lab report, which isn't what I'm going to do. Now, the experimental data is organized according to the unknown numbers. The unknown numbers are written 3x1, 3x2. What does 3x1 correspond to? It corresponds to a 3 and a 1. So if you had an unknown number of 311, 321, 331 on down the line, if it ends in 1, you have unknown number 1. If it is a 3x2, that corresponds to all the unknown numbers that were 312, 322, 332, etc. So that's the coding scheme for these unknowns. So you're going to look at your physical property data, which I'll show you in a moment, but it's all corresponding to what is the last number of your unknown. As I showed you, the NMR of the Ester unknowns are all in the April 16th folder. We'll go over how to interpret the NMR of an ester and how you're going to use that to determine the purity of the ester. All of the data that I'm going to give you is actual student data. I combed through old reports from the summer as well as from last fall. I'm going to give you a couple of pieces of advice having looked through those lab reports on things to do in this lab report to make sure that you get maximum points or minimize point deductions. The other thing is, before you start writing your lab report, you're going to need to determine the identity of the unknown ester. And you need to determine the identity of the unknown simply because you're going to use that identity to create your physical property chart, and also then you're going to use that to write the complete mechanism. If you don't know what the ester's identity is, then you won't be able to complete those. Okay, so let's move to requirement number 1. You're going to write a short background of the experiment that includes the overall goal of the experiment. The overall goal of the experiment was something like to synthesize an ester from an unknown carboxylic acid and an unknown alcohol and determine the identity of that ester using boiling point, microboiling point, refractive index, and also creating a 3,5-dinitrobenzoate derivative, which I will talk about. So once you know what the name of the carboxylic acid and alcohol that you made, then you're going to write the complete reaction mechanism, and I'll show you that in a moment. And since we only did the reflux in week 1, there's normally in the background we would have how you isolated the product, how you purified it. In this case, we didn't isolate and we didn't purify the product. So you don't need to put that in your background. However, you will have to outline how we're going to determine the identity of the ester. So here is the overall reaction that we did. You were handed a bottle, or you picked a bottle of carboxylic acid and alcohol in roughly 1-to-1 molar ratio, give or take. You use sulfuric acid as the catalyst. You reflux this reaction to form the ester and water. Now I'm going to talk a little bit about this reaction in terms of the reaction, and then in the next slide the mechanism. You may have already talked about that in lecture. I know I have talked about it, but basically the problem with this reaction is it is an equilibrium reaction. That is the problem. And so somehow, if we were looking for maximum yield, we would have to somehow push the equilibrium to the right using Le Chatelier's principle in order to make the maximum amount of ester. Typically what we would have done is we would have used excess acid, or we could have removed the water as it was formed. And in most cases, what we would do is use an excess of the carboxylic acid and then have the reaction go to completion. I'm going to be honest, I measured out 30 mils of carboxylic acid and alcohol, so whether or not we are in excess of carboxylic acid, I'm not quite sure. In the future, we would definitely run in excess carboxylic acid to alcohol. Since I know what the unknowns are, I could have figured out exactly how many mils of each to use. Removing the water is a little bit more difficult. There's actually apparatus that can be used to remove the water as it's formed. If you're an overly ambitious go-getter student or have an interest in this, there is something called a Dean-Stark apparatus that you could use to remove the water as it's produced in the reaction and the reflux, and that would push the equilibrium to the right. In order to get this equilibrium established, that is why we had to do a reflux, and without the acid catalyst, which came from sulfuric acid, the reaction would go nowhere. So if you forgot to use sulfuric acid, you would get no product because it's required as the catalyst for this reaction. Okay, so that's kind of an overview of a Fischer esterification reaction. Again, the big limiting factor here is the ester, is the equilibrium to form the ester. Now here is the mechanism for this reaction, and it's in your handout, and it's something that we would typically go over in the lecture. I know I've gone over it in my lecture class so that you can form the ester. Now I want you to write the mechanism of this reaction. So it says up here, and write the complete reaction mechanism for the esterification, including the acid catalyst, using your determined carboxylic acid and alcohol. Do not cut and paste this into your report. You will receive 0 points. I looked through some of the lab reports from last spring. I saw numerous people had done this. Sadly, the TAs did not take all of the points off. So you want to make sure that you write this mechanism without R groups with your actual carboxylic acid and your actual alcohol. Okay. Now, in week 2, what we would have done, and remember, we reflux this for approximately, an hour and 45 minutes or so, and then we put it back, we let it cool, we put it back in the bottle. What we would have done in week 2 is we would have done an extraction to purify. We'd have tried to purify this as much as we can. So, writing the equilibrium reaction out again, we would have alcohol plus carboxylic acid with the acid catalyst to form the ester and water. At the end of the reaction, at the end of the reflux period, we would have all of these components in our reaction mixture. So in our round bottom flask or in our bottle, we would have had all of those components. We would have had the carboxylic acid, we would have had the alcohol, we would have had sulfuric acid because it's a catalyst, it didn't go anywhere, and we would have had water. So how would we have basically, well, and I forgot the most important part, we would have had the ester. So how would we isolate and purify the ester from all of this? Well, here's what we would have done first. What we first of all would have done is we would have extracted this mixture. We would have extracted it with sodium bicarbonate solution, an aqueous solution of bicarbonate. Again, would have been sodium bicarbonate. Now, carboxylic acids are the only ones in this mixture that will react with bicarbonate. And the bicarbonate would have deprotonated the carboxylic acid. We would have made the carboxylate salt. The salt just means it's the deprotonated carboxylic acid, and we would have formed carbonic acid. Now, the problem with carbonic acid is it is unstable. It would break down into CO2 and water. So what we would have done is we would have taken our separatory funnel and we would have had 2 layers. We would have had the ester layer on top, and we would have had the water and probably some excess bicarbonate. And what would have happened is the bicarbonate would have reacted with the carboxylic acid, so any excess carboxylic acid down here would be formed as the salt. That's an ionic compound, and so as an ionic compound it would have been in the aqueous layer exclusively. What would have happened to the sulfuric acid? The sulfuric acid also, any sulfuric acid left over would have reacted with the bicarbonate as well, and it would have produced water, and then it would have ended up as a sulfate ion. And so we would have NaH plus that was converted to water also in the bottom layer. The only thing that would remain in the water layer, so of these compounds, we would have removed the carboxylic acid, the sulfuric acid, of course, any water that was produced. All we would have left over is the ester and any unreacted alcohol. Alcohols cannot be deprotonated by sodium bicarbonate. The biggest problem that we would have had here with this reaction is we would have had to add the bicarbonate. It would have fizzed, and we would have had to swirl it around until we quit fizzing. The fizzing is the CO2 evolution, and we would have put the cap back on. Then we would have gently turned it upside down, immediately vented, and then we would have gotten more aggressive with the shaking once we knew that there was no more CO2. I would have cautioned you about that in the lab, that if you added the bicarbonate, immediately put the cap on, and started shaking, you would be wearing most of your product home. And with my luck, I would have been standing right there, and so you would have sprayed me with your product as well. So fortunately, I guess we didn't have to worry about that, but this is what the extraction, our first step, would have done, is it would have removed everything but ester and alcohol. Then in the second step, what we would have done is we would have set up a standard distillation apparatus with our thermometer in the right position, and then our condenser, and we would have added then the ester and the alcohol, some boiling stones, and we would have distilled then the ester versus the alcohol. Now, when we're doing our distillation, we hopefully would have separated these two, because an ester is a dipole molecule, a polar molecule, and so at best it would have had dipole-dipole interactions, whereas the alcohol has hydrogen bonding. What does that mean? That means in general the boiling point of the alcohol would have been higher than that of the ester, and so if we used the right temperature, we would have distilled off the ester while leaving the alcohol behind. As you're going to see from real student samples, that does not always happen, and there will be alcohol in the final product, and so what we need to do is analyze that and determine what percentage of that alcohol it is. Okay, so we would have separated by distillation based on the boiling point difference between your ester and your alcohol. And if you're not convinced of that, when you finally determine the structure of your ester, look at the boiling points in the table, in your physical property table, and it will give you an idea of how much higher the boiling point of the alcohol would be over the ester. So that's what we would have done in week 2. Of course, after we were done extracting, we would have dried with not sodium carbonate, with sodium sulfate. We would have dried it. Actually, we may not have even used. We would have either used sodium sulfate or we would have used calcium chloride to do our drying. Then we would have gone ahead and done our distillation. Okay, so that's how we would have gone through. And I did not put a separation scheme in this lab report, although you could very easily write a separation scheme for this. Okay, so that's what we would have done in week 2, and we would have had purified ester, as purified as we can get. Okay, so what would we have determined in our distillation? We would have determined the boiling point of the reaction. We would have measured the boiling point at 25% distillation, at 50%, and at 75%, and those would have given us a range of boiling points in our distillation. And you have to remember all the way back to experiment 1 and 2 when we did that to determine the boiling point range for the liquid. So when you see ranges in the physical data that I'm going to show you, those ranges came from students measuring when 25% had distilled, 50% distilled, and when 75% had distilled. Okay. So what that does is that gives us the boiling point of our unknown mixture. So for the molecule that I'm going to show you, and I have to remember exactly what it is. Let's just make something up. Let's just say, for instance, none of these are potential unknowns. So let's say I would have measured a boiling point between something like 122 and 100 and 44 degrees, what I would do then is I would probably use a range of plus or minus about 5 degrees from each end, so plus or minus 5 on the 132 and plus or minus 144, 5 on the 144. So basically I would be looking at something in the neighborhood of this range of potential unknowns. Okay, so that kind of narrows it down a little bit in terms of what my unknowns would be. Okay, so what would we have done in week 3? Well, in week 3 we would have gotten some further physical data to allow us to make the measure, or allow us to determine the unknown. And what we would have done is what's called a transesterification reaction. It's a little bit different because it's a little different than we talk about in class in terms of this transester if spelling's important. So in this case, what we're going to do is we're going to react our ester, our unknown ester, with an excess of 3,5-dinitro benzoic acid. And what will happen then is that the alcohol portion of the ester. Now remember, esters were made, we made the ester from a carboxylic acid portion and the alcohol portion. What it would do is it would replace our carboxylic acid portion with the 3,5-dinitrobenzoate, or 3,5-dinitrobenzoic acid, and then this part would be from our ester. And this carboxylic acid would also be from our ester. And this is actually what is called a derivative. A derivative is a compound that you make to help in determining the identity of the unknown. So in this case, that's what would happen is we would transesterify this. We would turn one ester into a second ester. Now, if you're curious about the mechanism of this, what would have happened is we would have taken the ester that we had and we would have used some sulfuric acid as the catalyst. So looking at the mechanism, and you do not have to include the mechanism in your reaction, but I'm going to show it to you, is we would protonate the carbonyl first to form that oxonium ion. And then what would happen is the 3,5-dinitrobenzoate, 3,5-dinitrobenzoic acid. The OH group on there would act as a nucleophile and come in and attack that protonated carbonyl. And what that would do, and we should probably have equilibrium arrows in all these steps, what that would do is that would then create the OH. Down here we would have an OH now with our carboxylic acid part. Remember, we always had the entire nucleophile here, so we have that. Then we would, up here, we would have our ester. Then we would have a pair of electrons move that way, so we would regenerate the catalyst, H+, so we would lose H+. And then what we would have is we would have this species. Now at this point in the equilibrium, there's 3 oxygen species that can be protonated. If you were to protonate the oxygen that we just added, then what would happen is the system would reverse itself, which is why there's equilibrium arrows there. If you were to protonate the OH group, water would leave, but I can't get to a final product because I'd have a plus charge here, but there's no proton to lose on either one of these oxygens. So the next step that would happen to get us moving forward is to have the OR group of our ester react with the H+. Okay, so once we have this, we're going to protonate that OR group, and that's going to leave. So I'm going to form the OR group here with the H and a plus charge there. That's going to leave the OH up here. And then again, I'll have my 3,5-dinitrobenzoic acid part down here with my nitro group there and my nitro group here. And then once this, and let me erase that. So let me write the bond in explicitly here. If I write the bond in explicitly, then what will happen is this. This pair of electrons will move there and the alcohol will leave. And I will end up with this compound initially. Now remember, that right there is my R group in the original molecule. Now you may say, wait, you're not making what you should make. True. This is a carboxylic acid anhydride. So what would happen then is that alcohol that I just freed up, which is the alcohol that came from our product, is now going to react with this anhydride, only it's going to react with the 3,5-dinitrobenzoate portion of this molecule. And remember, there was excess 3,5-dinitrobenzoic acid present, so this alcohol can do one of two things. What it can do is it can react with the other equivalent, or with the excess of the 3,5-dinitrobenzoate, and I think that's what we're going to do. So once I form this anhydride, let's forget about it. What's going to happen then is that the alcohol that just got liberated is going to react with the excess of the 3,5-dinitrobenzoic acid in the presence of the H+, and through a standard Fischer esterification, what I'm going to end up doing then is I'm going to end up adding that OR group to the 3,5-dinitrobenzoic acid part to make the transesterified product. This is a really ugly mechanism. If we were over here at this anhydride part, the alcohol could react with, this alcohol could also react with this side of the anhydride and then make the same transesterified product. But let's make it simple in terms of the alcohol reacting with the excess of the 3,5-dinitrobenzoic acid. So that's how we write the mechanism. It's not a clean mechanism by any stretch of the imagination, and there would be better ways to do this. So the idea here is that this 3,5-dinitrobenzoic or benzoate ester has R alcohol from the original ester molecule. So what we do is, in this table are the melting points of that 3,5-dinitrobenzoate compound. So for instance, down here before we were looking at boiling points from 127 down to like 148. And I don't believe there's any molecules that could be yours in that. So once we have our range from our boiling points, from our boiling point measurement, then what we could do is we could compare the melting point if we took each one of those esters and we converted it to the 3,5-dinitrobenzoate derivative. And so what should happen is, let's say we measured a 74. Let's say we had a measurement of 74 to 76 degrees for our melting point. Once we went through that reaction and isolated our product, well, we could slowly but surely begin to go through and say, yeah, maybe this one, if it's a little high, or this one could be potential unknowns by comparing that ester, the ester of the 3,5-dinitrobenzoic acid. So basically these derivatives are taking this alcohol group and adding it on to the 3,5-dinitrobenzoic acid. So that's where these melting points are coming from. So it's another piece of physical evidence to help us narrow down the potential list of unknowns. Okay, and so that's what we would have done is we would have prepared this. This would have precipitated from solution, and we would have measured its melting point, and then seen which derivative or which derivatives had melting points that were close to that to help narrow down our initial list of molecules. Of course, then we can now use our refractive index on the ones that are left to see, okay, which ones are good candidates for that. And so we would have measured the refractive index using one of the little refractometers. In week 4, we would have measured the refractive index, which we would have just used in our chart to help narrow down the potential list of unknowns. We also would have done a micro boiling point, and the idea was to get technique in measuring the micro boiling point. Micro boiling points are great if you have a small amount of liquid and you need to know about the melting point or the boiling point of the liquid. You don't have enough to do a distillation. So the way you set up a micro boiling point is we use this thing called the teal tube. The teal tube is filled, this is filled with mineral oil or silicone oil. You use a Bunsen burner to heat it. By heating the oil, there's a convection, so essentially you're heating the liquid. The liquid is placed in a small capillary, and then you use like a melting point capillary. You drop it in so that the closed end is at the top and the bottom is the open end. So this would be the open end. And then what we would have done is we would have had a thermometer right next to, oh no, somebody's using a mercury thermometer. I hope they don't break it, because then I'll have to shut down the building. Well, that's not a problem now, is it? So we use this thermometer, and it would be close enough so the temperature of the liquid would be accurately measured by the temperature of the thermometer. So what happens in this process is we heat up the solution, and then we would see the following. So I'm going to go out of here, I'm going to keep all of my writing, and we're going to go to the website, and we're going to look at the video here very quickly.
I'm having trouble hearing you.
And we're going to measure.
The equipment needed in order to determine the boiling point of a liquid includes a thiel tube with a high boiling oil, the level of which should be just above the thiel tube sidearm. A small test tube filled with no more than 0.5 milliliters of your sample, and a capillary that is open at one end are also needed. A glass thermometer, which will be attached to the test tube with a rubber elastic, is required as well. The apparatus is heated with a Bunsen burner.
Okay, so yes, it is heated with a Bunsen burner, and now let's see what actually happens.
The elastic
So let's go forward
Eventually,
here.
quite quickly as the oil begins to heat up, a small and slow stream of bubbles will exit from the base of the capillary. This is the release of air which was initially present in the capillary, and is not the boiling point of the liquid. Eventually, a rapid and continuous stream of bubbles is observed. At this point, the vapor pressure of the liquid has exceeded atmospheric pressure, and the boiling point has been surpassed. Stop heating and watch the base of the capillary closely. As the liquid cools, its vapor pressure decreases. When the vapor pressure of the liquid reaches atmospheric pressure, the boiling point is reached. As the pressure drops just below atmospheric pressure,
so notice that in this case the liquid started to rise up into the capillary. I don't know what, capillary is what she was saying. This is I call it a capillary. So as the liquid goes back up into the capillary, the minute that it would have started rising up, we would have measured the temperature, and that would be the micro boiling point. So micro boiling points don't have a range per se. This is a very difficult technique to do. So what you may find is that the micro boiling points that you have as your data may or may not match up well with the distillation boiling point that you got in, or that you would have gotten had you have distilled your product after extraction. So you can go back and you can read this video or watch this video, and they'll take you through all of the entire steps. But that's how we would have measured a micro boiling point. Okay, so going back to this slide then, once the liquid starts to rise up into the capillary, that's when we would have measured our boiling point in degrees Celsius. Okay, and we would have carefully heated the mineral oil over here with the Bunsen burner until we saw that stream of bubbles come shooting out, and then let it cool, and as soon as the liquid went up and in, boom, that's our boiling point. So that's what we would have done, is to measure the micro boiling point. And again, this is a very useful technique to measure the boiling point when you only have a very small amount of liquid. And depending on the type of melting point apparatus you have, you can sometimes do this in a melting point apparatus. Unfortunately, ours are not very suitable for this, which is why we would have used the teal tube. Okay, so once we have the micro boiling point and the distillation boiling point, that allows us to determine our unknown range. Then we have the melting point of the 3,5-dinitrobenzoate, which will help us narrow it down, along with our refractive index. We should have just a couple of candidates at the end of that, all the physical data, in order to then determine what the identity of the unknown is. And what I'm going to do here is I'm going to go back out into the Canvas site and just show you that the physical data, there will be a physical data block here. There is not one right now. I can show it to you though on my computer. Hopefully there's no FERPA violations going on, but the Ester's experimental data will look like this. It will have the unknown number, the distillation boiling point, the micro boiling point, and again, there may be a difference between those, so your range might have to include both sets. The refractive index that was corrected to 20 degrees Celsius, and then the melting point of the 3,5-dinitrobenzoate derivative. So if you had unknown number 333, you would use the 3x3, and you would use that set of data in order to determine your identity of your unknown. Okay, so that table will be in Canvas. Okay. So in terms then of writing out the experimental procedure and observations back to the lab report, what you would have done is you would have then write out the entire week one procedure, which was the distillation, include all your observations. Unfortunately, there is no data. There are no data for that part of the experiment because you just had the bottle and you didn't measure the mass, most likely, of the product because you don't know what it is and you can't therefore determine the percent yield if you don't know what you're dealing with. So in your tabular summary of results, you would provide the tabular summary of the data, the appearance of the product after the reflux. Note that many of them had different colors. You're going to note the other data that are provided in the table that I just showed you, including the boiling point, the the melting point, the microboiling point, and the refractive index. So you're just going to include that in the table. The only data that you will have is the observation of the appearance of the product. Then what you're going to do is you now have basically a list of potential unknowns. And you might be down to one or two, but the ultimate determination of the product's identity is going to be proton NMR. So let's go back and let's talk a little bit about how do you determine the structure of a ester NMR. Now we've had some problem sets on that, and so let's take a look at some real theoretical data for an ester that no one has. Okay, so what I have is I have a structure that I put into my iPad, and I used a program called Orange NMR, which I believe is free, and it predicted the proton NMR spectrum for me. These numbers here are my integration values that you would normally see in all of the problem sets that I gave you that actually had numbers. So looking at this, we know we have an ester. And I'm going to go ahead and write out the structure of subgeneric ester, and we'll go ahead and talk about how you determine the structure of an ester from NMR data. There's a video on this. If you go into my YouTube site and you look under the CH224, or just search my name, JCU, and Ester NMR, and I think you'll find that video. But here is what we are going to look at. So here is the structure of an ester, and I'm going to erase that hydrogen because I don't know that I wanted it to be there. Okay, so here is our structure with H's on both sides. Now, the way we determine the structure of the ester is this. Realize that the hydrogen attached to the oxygen shows up between 3 and 5 parts per million. And the hydrogen attached to the carbon next to the carbonyl is going to show up between 2 and 2.5 parts per million. So that's where we start. Let's look down here, and this is again a simulated data. I'll show you what the real data for this compound looks like in a moment. All right, so here's our integration ratios. Let's call the smallest value 1. So this would be something like 1H, 2H, let's call that 2H, 7H. Well, we know we can't have 7 hydrogens, so this is probably going to be somewhere in the neighborhood of 6H, and then 3.5. Let's go ahead and call that 3H. Now, in the NMR problems, you always had a molecular formula to work with. We don't have that here. Our expansion of this peak shows that it is a multiplet. Down here, looking at the expansion, we have a triplet. we have another multiplet, a symmetrical multiplet, which means that that it is in between two non-equivalent groups, but we don't have overlapping peaks. And then here we have you can clearly see here it's a doublet. It's a little bit harder to see over here. And then we also have a triplet again. Okay, so there is our NMR data for this molecule. Now, that means that this is going to be most likely a CH group. This is going to be most likely a CH2 group, another CH2 group, 6 hydrogens total. Hopefully you've done enough problems to know that that would be most likely 2 CH3s and then another CH3 here. So these are our pieces that I'm going to go ahead and put together. The data that I gave you in terms of NMRs, which I'll show you some real student data here, the integration ratios aren't beautiful. They don't always match up, particularly in the sets that or the example of this molecule that I'll show you in a moment. So what I have is a CH, a CH2, a CH2, 2 CH3s, and a CH. Okay, now the peak here at 5, that's the group that is next to the oxygen. So the group next to the oxygen is a CH group. The group here at about 2.5, that's between 2 and 2.5. That means on the other side I have a CH2 group, because the groups next to the carbonyl are between 2 and 2.5 parts per million. Okay, so we've got the position of the CH, we've got the position of the CH2. Looking at these two CH3s, what are they? They're a doublet. How many neighbors do they have? Well, if you're a doublet, it means that n plus 1 equals 2, n's the number of neighbors, so this doublet is next to a CH, which means we have an isopropyl group. So we've taken care of those two, and then what's left over is CH2, CH3, a CH2, CH3 group. This CH2 is in between a CH2 and a CH3. That means it would be a multiplet. This CH3 is next to a CH2, which means it should be a triplet, and that's exactly what it is. So this is isopropyl butyrate. So the naming of an ester is alcohol part first, then carboxylic acid part, plus the ATE ending. So the alcohol would come from, in this case, this would be an isopropyl group. And over here, it's the 4-carbon acid, so that would be butyric acid, so that would be butyrate, which is the 4-carbon acid. Just for sake of argument, a 1-carbon acid would be called formic acid. There are no formates in this, but that's formic acid. A 2-carbon acid is called acetic acid. So acetic acid would become acetate. A 3-carbon acid would be propionic acid. So this would be a propanoate, most likely. This would be an acetate, and this would be a formate. And basically those are your only choices. I chose this one because we've eliminated butyric acid. We eliminated butyric acid this semester because butyric acid just it reeks. And so we got rid of that, and we only used acetates and formates. As far as the alcohol group goes, could be anything. So this student unknown is isopropyl butyrate. And so that's what you have to look up on the chart. So if we go back to the chart, we would find we were looking for isopropyl butyrate. Oh, look at that. I happened to choose correctly in the original range. So there would be isopropyl butyrate. So if I got that structure, I'm going to expect a boiling point around that area. I don't know, give yourself 10 degrees. Then the refractive index should be really close to that, and the melting point of the derivative should be close to that. But the definitive answer of this, if this was a student unknown, the definitive answer is this is isopropyl butyrate. Okay, and so that's how we make our identification of esters. All right, here's real student data. Before, when I came to work at home, I copied all of our NMR files onto a thumb drive. I found a free NMR processing program, which I have on my computer. And so I then had to search through tons and tons and tons of data until I found one of Dr. Kwan's sections where they had actually measured a bunch of student unknowns. And they had actually saved the spectra, which I will do from now on because I don't normally do that. I just print it. So here is student data for isopropyl butyrate. You can see it's not very clean. It's not as clean as the spectrum from before. There's just a multiplet, triplet, multiplet, doublet, triplet. In this spectrum, we've got a lot more. So what's going on here? What's going on is this is unreacted isopropyl alcohol. So the distillation process that occurred in this experiment did not remove all of the isopropyl alcohol. So in your spectrum, there's one that had a sufficiently different boiling point of the alcohol and the ester that it didn't show any unknown, or didn't show any unreacted alcohol. But in this compound, in this molecule, what you see is these peaks, and then over here this doublet has an extra peak here, and this triplet has some extra peaks there. Those are all isopropyl alcohol, unreacted product. And that's going to throw off the integrations of these two peaks, because in addition to the ester, we also have a little bit of peaks showing up. I tried to integrate them as much as possible, but there's only so much you can do. So these integrations might be off a little bit. So when you're looking at your spectrum, these small peaks, these smaller peaks that are next to the esters, those are unreacted alcohol. So you're going to mark those. Now what I'd like to do is, okay, I know there's unreacted alcohol in here. What is my percent purity of this ester? And what I would do is I'm going to take and I'm going to use the integration ratio of the ester divided by the integration ratio of the ester plus the integration ratio of the alcohol impurity. That total integration, and then multiply by 100, and that will give me the percent purity for this particular sample. It's kind of like what we did with GC last semester. So in this case, I have 9.999 over 9.999 plus 2.637 times 100. So if I pull out my calculator, we've got on the denominator, we've got a grand total of 12.636, so 9.999 divided by 12.636 equals, times 100 is going to equal 79.1% pure, which means it had 20.9% alcohol in it. That 20% alcohol might very well throw off the boiling point and the micro boiling point. It might even throw off the refractive index as well. So just be aware of that as you're determining the structure and the purity of your unknown. You're required to do this. There's only one unknown that didn't have any that I could find that didn't have any alcohol, but the rest of them did, and they're all integrated. They're all showing up. You could do the same thing down here for these two triplets of the alcohol. You could say that the purity is 21.195 over the total of 21.195 and 4.037, and that would have given you that'd give you a second number, and then you could average those out. So that's how you're going to determine the structure of the molecule using your NMR, and then also using the NMR determine the purity of the product and how much unreacted alcohol is in there. And if you follow the directions, it will tell you to assign all of the products NMR, assign the peaks. Once you have the structure, you're going to have A's, B's, and C's like you did in the NMR homework sets, and then you're going to identify any peaks corresponding to the alcohol, and then for each of the ester peaks determine the ratios of whether they're 1H, 2H by dividing through the smallest integral value. So that's how you're going to analyze in the data, and you can do that directly on the NMR. Write directly on it, take a picture of it, and incorporate it in your report. So then the final part of the report is a discussion. In the discussion, what you need to do is first of all identify the ester. I didn't say this. The first thing to put in your report is include the unknown number. I mean, we'll figure it out. We'll figure it out from the data that you use. But make sure you include the unknown number, because there is a deduction for not doing that. And that was something that students in the past have not really done a good job of. So try and do a better job this time. Now, the ultimate determination of the identity ester has to come from NMR. So whatever your identity is, it better be consistent with the NMR. Then you're going to discuss, well, how did you determine the structure of your ester from the NMR spectrum, the integration ratio, the chemical shift, the multiplicity of each peak? How did that make your assignment? Type it out. Type out your reasoning. Are there any integral ratios that deviate from their ideal value? We saw that in the real, even in the computer-generated data, they weren't quite, well, okay, I kind of made that data up, but I based it on the real data. The real data isn't quite matching up for the compound I showed you. Why? In the NMR you have, is there any evidence of why the integration values aren't quite what they should be? Hint. Go back 10 minutes and watch the video again, because I think I gave you some ideas. Then discuss whether the boiling points that you determined are consistent with the identity from the NMR. How close to true value are there? when you're doing that, make sure you cite the data. So it's not sufficient to say, oh, the boiling points were close. Not good enough. The boiling point was 25 to 27, 125, 127, and the literature value of the ester I determined it to be was 127, 129, something like that. Do that. How consistent is the melting point for your unknown? Does it confirm the identity? From the data provided, how pure was that ester? Also in here, go ahead and include your refractive index and how close it was as well. So also include the refractive index, which is the ND20. How close was it? Again, these are all student-derived pieces of data, so they're not data that I just made up. They're from student reports. I may have modified them slightly so that everybody would get the correct answer if you do the analysis properly. Okay, so also include the refractive index as well. Okay, so that's what is going to go into your report. That's how you analyze the NMR. That's what we would have done. This video, now that you're watching it, means that it was posted in the Canvas folder. It will be posted in its own page, just letting the cat out of the bag. When a video is posted in its own page, it means I can see whether or not you watched the video. I can see what parts you skipped. I can see how long you watched it. So if you were watching it at triple time, I can see that. Just letting the cat out of the bag. So make sure that if you just fast forwarded, well, if you fast forward this, you don't know that, and then I'm going to send you a terse email. So, but I can do that, and I may very well be curious enough to see who's watching and who's not. Okay, so that's our report. If you have any questions, post them on Piazza, email me, schedule a meeting. But this is what I would like for the esters report. It is not. It is going to be due. It's not due the same week as the benzocaine report, which is the Thursday after our quote-unquote Easter break. It will be due the week after, so the deadline, the drop box, the due date will all be on Canvas so that you can take a look at it. Okay? Any questions? Like I said, email and Piazza or schedule a meeting. Okay? All right, so we are done here. I know it's a little bit over an hour, but well, I haven't edited it yet. It'll be under an hour when I'm done editing it.